All right, I'm gonna get started. As always, if you can't hear me or something sounds like it's not right with the microphone or the sound or something, just let me know in the chat. But otherwise, yeah, let's get going. Take a quick moment just to do a bit of a recap. Over the last couple of streams, I've been building out this like kind of driver stack for the bus pirate, and the bus pirate is this red device. And let me switch view. This kind of red device I've got here with some lights on it, and over here we've got an SD card wired up with a wiring harness. Yeah, and this device, basically what it is it's a multi-protocol bus device. Yeah, it's kind of like a Swiss Army knife actually for kind of reverse engineering and doing hardware stuff. And what this is enabling us to do basically is to connect via USB to this device, and then it opens up these channels that we can talk to other devices with. So we can talk about SPI, we can talk about I2C, we can just sort of control the pins directly and talk like whatever we want, as long as we can control the pins fast enough and with that kind of thing. So we can do that. We can talk a protocol called one wire, which is where, surprisingly enough, you use one wire to communicate between different devices. That one's pretty cool. But right now we're focusing on SPI, because SPI is the basis of the SD card. It is one of the ways in which we can talk to an SD card. And yeah, in the last stream, what we actually did was build up the basis, the initialization process of talking to the SD card. And we got it to the point where it worked. We had it all set up, and we're kind of ready to start reading and writing information to it. Hey Max. Yes, so today what we're going to do, well, what I've done here is I've actually, set up a small goal, and the goal is to read the contents file. I guess I meant of a file. Read the contents of a file located on the SD card. That's it. That's the goal. And this SD card is formatted using the file system FAT32. So that's that's like a Microsoft designed file system, I believe. And yeah, we're going to got like 3 agenda items. Agenda item number 1 is to fix the if statement. So here in the code, and let me turn this off. Is this working? Oh yeah. Let me just make that work really quickly. I can get by without it for now. All right, so somewhere in this initialization process, and let's go to the code because I almost didn't show it there. I also realized that I didn't show this whole thing. But yeah, so this is a page, got the goal and some to-do items. All right, so I wrote this if statement, and someone actually said on the stream, "Hi Ghost War, how are you doing?" Ghost War RO. I wrote this if statement, and someone in the chat said, "Oh, this looks wrong," and I was like, "Oh, it's it's not wrong. Don't worry. It's right." And of course, it was actually wrong. So what this is actually testing for is that we got the right, we got the response we were expecting. It's kind of doing the inverse, right? It's expecting, did we get the response we were expecting? And what I should have done here is make this an OR, and then this is like one statement. So if we didn't get the response we were expecting, or we did get the response we were expecting, but this part of the response and this part of the response didn't match. And I guess it could also be an OR here, right? So I guess all of it is an OR. So the response didn't match, this part didn't match, or this part didn't match. If any of those 3 conditions didn't work, then it's wrong. So I need to fix that. Does this code run from Node.js or what? Yes, this code is running from Node.js. So I'm running it. Node.js talks to the bus pirate, which is this device I have on my desk. It talks to that device over USB serial. And the bus pirate enables us to, like, via sending stuff over the serial port, we can command the bus pirate to speak other protocols for us. So we send our data over those protocols. The protocol in this case is SPI, so we've got this special class, which is an SPI mode class. That allows us to send SPI messages to devices. So in this case, we're sending them directly to an SD card. And yeah, this is all happening in Node, so this is building up. You can actually build, you know, the serial port is one of the easiest ways to talk to any hardware. It's also one of the simplest protocols, but it's not the only way. You can do a lot of kind of low-level programming with Node, a lot more than people seem to think. You can actually write full USB drivers in Node using libUSB, for example. Nigel says, FAT was the file system of MS-DOS from the 1980s. Yes, it was. And we're hopefully going to see some nice historical remnants today as well. Although it's still widely used because of what we're going to see here, it's a relatively easy file format to interact with from an embedded perspective. But yeah, I mean, like, modern file systems make other kinds of trade-offs. They can have complex systems behind them, as long as they're able to deliver on a lot of other features, like, you know, making sure your data is properly stored and doesn't get fragmented and all of that kind of stuff. Whereas FAT is, like, you know, it's quite a simple file system, and it's relatively easy to kind of interact with over these things. So that's what we're going to see. Alright, so the first thing to do is fix that if statement. That one's checked off the list now. Now the next thing to do is going to be add a new method to the SD card driver class, and that's going to be the SD read block method. And that's going to do basically what it sounds like. That's going to enable us to read a block of data from the SD card. And as a small reminder from last time, basically, this driver is only going to support what are known as SDHC cards, so high-capacity SD cards. And when you speak to high-capacity SD cards, the block size is 512 kilobytes. Sorry, 512 bytes, half a kilobyte. Yes, so when we read a block, it's always going to be 512 bytes. That's something to keep in mind. Go straight for ZFS. Yeah, that might increase the complexity level somewhat. Max says, I literally formatted a drive with FAT32 yesterday. Still in use. Yeah, 100%. Still in use a lot. Everything supports it. You can plug it into anything, and it's also easy for boot media. That's one of the other things we'll see. Like, you can boot directly from this format. Alright, so let's first, before we do anything else, let's write this SD read block. So this is going to return us 512 bytes, and let's zip to the web browser, and I've got a page open from PJRC, which are the makers of the Teensy board, and they have a nice page about FAT file systems, which we're going to reference. But first we're going to go back to this Elmchan page, which is an amazing resource. So Nate says the path to hell is paved in linked lists. Yes, we're going to see some linked lists today. I think because of the way I've set this up, we're not going to need to do too much delving through linked lists, but like actually even to get to the point where we know where the file is, we're going to have to follow quite a lot of pointers at least. Not quite formally linked lists, but is there a difference between SDHC and SDXC, or would both work for what you're doing? I believe in this case it wouldn't make a difference because we're speaking to the SD card in SPI mode, and when you speak in SPI mode, you're bumping the level down of the SD card a lot. The SDHC and the SDXC, they are actually much more advanced devices internally, and when you speak in SPI's native mode, when you speak in SD's native mode, the speeds go way up, and you can just start pushing tons of data through the SD card. And I believe that the when you start going to those high capacity cards, some of them even have more pins because they allow more signaling to happen at the same time. But for the SPI mode, it's all really simple and it's all really slow. So it's for our case, it would make no difference. I mean, if you want to do this at home, which you totally can, yeah, you could basically use anything. You might need to make some adjustments in the driver, because I've made these error conditions around SDHC, but if you follow this page, this ElmChamp page, you can figure out how you should actually speak. If you're going to do a lower capacity card, you can do it that way. If you're going to do a higher capacity card, I think it wouldn't make a big difference. That's my understanding of it anyway. Okay, so what we need to do is to implement one of these commands. And the command we are going to implement is command 17, which is read a block. And read a block will return us an R1, but then it's also going to return us a few more things. So let's scroll down. I believe they've got a little bit more information than this. So yeah, so here we can see the single block read. So if I send command 17, sometime later we get a command response. That's going to be our R1 response, so just telling us, you know, the basis, what R1 tells us, which is just kind of what the state is. Did we get an error, or are we in an idle state, or that kind of thing, kind of just the status. And then a little while later we're going to get a data packet, and a data packet consists of a couple of different things. So it's going to consist of a data token, and that's going to be one of these three things depending on which command we send. Then it's going to be a data block, and in our case this is always going to be a 512 kilobyte. I'm going to keep saying this, a 512 byte block. And then we're going to get a CRC, a 2-byte CRC. So CRC 16, in this case we're not going to do anything with that. We could check it. We could actually, you know, at some moment either build CRC16 or, you know, install a module. But I'm not going to do any of that today because I'm pretty sure we're not going to get corrupted data. It would be really funny if we did, but I'm hoping that we won't. So we're going to get this data token back. We're going to expect that in this case to be FE, right? Because we get all ones and then a 0 as the LSB. And then we're going to get our data, and then we're going to get the CRC. So let's implement this. I think I have command 17 in this big list of commands that we robbed from the Arduino SD library, command 17. So we're going to use send command. So first things first, we'll send the command. So that's going to give us back an R1 response. Did I capitalize R1 in init? I'm just wondering if I should do the same thing here. I did, so let's do that. I don't think we need to reassign it, so I won't. This.sd send command. The command we're going to send is command 17, and the argument we're going to send is the block number that we're going to read. So when we speak to the SD card, we're going to use something called LBA, which I believe stands for logical block address. I could be wrong about that, but that's what I think it stands for. Oh, here's some information about SDXC, by the way, Greg. So there's definitely some stuff you can find there. LBA, let's see, LBA. The data read-write operations are commanded in block addressing instead of byte addressing. So we're like, when we give an address of a block, we're actually talking about a 512 byte section. So if we talk about block 0, that's going to give us the first 512 bytes. If we talk about block 1, we're going to get the next, like the preceding 512 bytes. So yes, that is how it's going to be. So let's take an argument here. I'm just going to call it LBA. and we will pass LBA as our argument here. And this isn't an async function, so we can't await. Now we can. At this point, I'm not sure exactly what R1 is going to give us. I think it's going to give us probably that we're in the idle state or in the ready state. Yeah, I'm not exactly sure which one's going to come back. So maybe we will first... Well, we can just log out what R1 is and then kind of assume that it's working correctly, and we'll just kind of do the next steps. So as per this this diagram, you see that there is going to be some time before we get this data back. So so we need to wait for data available again, and we have this await response, and the response gives us the first thing that is an FF, and so this should work for us. We can actually just get the first byte. And one nice thing about this, and I don't know if this is kind of incidental or if this is part of the design, logical block addressing has a Wikipedia page. Okay, Nigel, yeah, so it probably is logical block addressing. I think that's what I said. So yeah, I think that makes sense. The byte that we're waiting for is actually going to be our data token, so that's actually quite useful. We can actually get the data token, and we can do await this.sd await response. Should come back pretty quick, and then let's log that as well. Data token, and it should be equal to FE. So let's just check that. And then once we have the data token, we can just receive 512 bytes. So let's get our block. That's going to be await this.sdrx. And we want 512. Then we have a block of data, and we then need to get the CRC. And I believe, is it mentioned here? I'm not sure where I read this. It may have been in the spec. Hey, welcome, Abhishek. Really glad you can join. I think I read it in the spec that you really need to receive the CRC. The SD card actually expects it, and it kind of considers it a problem if you don't also then receive the CRC. And remember, in SPI, in order to receive something, you need to send something at the same time. So the card knows that we're receiving because we have to initiate that transfer ourselves. So we will grab the CRC and just log it out anyway. So we'll do const CRC, and that's going to be await this.sdrx with 2, because it's a 16-bit CRC. So let's console log the block. We'll just see what the first few bytes are, and we will console log the CRC. And then for now, let's actually also just return the block. So too many logs in there for really to be useful, but it should be okay for now. And probably actually init has a bunch of logs as well. Maybe not, maybe I clean them up. All right, so let's just see what's on block 0, because that's the first block. So block 0, and we can get that by then await sd.sd read block. We want to read block 0. Okay, let's just run this. So I have the device plugged in already, and I'm going to run the code with tsnode sd driver. All right, we didn't get a response in time, so something went wrong. 140, so that's not even in this part. that is, didn't get the expected response during init. Alright, so I'm gonna just take everything apart, plug the wires in securely, and make sure it's all like maybe it's shifted around a bit in the last week. So, oh yeah, these wires definitely feel loose. I think when I picked it up to show the camera, that was a fatal mistake. The wire's going to the SD card, so the light still blinks. Alright, let's try again. Alright, so that's not quite right, but I think we got a little bit further than before. We got to 190 this time. 190 is actually here in the read block. So I guess 190, that is here, awaiting the data token. Okay, let's just wait a bit longer. I'm arbitrarily putting 4 seconds there, but I think that's like too much. Unplug, try again. Hopefully this is not just like really flaky wiring. No, I don't think that worked there. But what? Oh, so I'm logging R1. Is this the log that's coming back for R1? Or is this? Yeah, because we're so. Oh, I know what's going wrong then. Maybe. Yeah, this is kind of confusing. All right. Let me take a look. Oh, yeah. I'm just looking at my backup code because I'm trying today to keep the stream relatively short in comparison to some of the previous ones, and I know exactly what I've done wrong now. So in Spy, you need to set this line called CS chip select in order to tell the device that you're going to speak to it, and we're not doing that. So we need to do that. So that's going to be await this dot spy, or sorry, how do we do this? This dot spy dot chip select enable. And then at the end of all of this transfer, we'll disable it as well. All right, that was probably the issue. So unplug that, plug it back in. Seeing as it got all the way to the previous point, hey, that looks good. All right. So we got 0 back. Wait, you know what? I think I'm doing this wrong. I think sending a command, this is not how I should send the command. I should do this, send the command, and then R1 is going to be an await response. Let's get rid of these timeouts now. So this is going to be the R1 response. And then we're going to await the data token. So we're getting there, and I'm pretty sure like this is looking good. This is looking like good data to me. So I think that was just a little bit wrong. I'm going to try this one without rebooting the device because there should be some way of doing it in software, and every now and again it works properly, so let's try that. Alright, that looks good. That looks way better because here we got our FE comparison coming back. And we got this giant buffer of stuff, and we got a CRC response. So that's looking good, and I think the good way of the good way of like checking this out is going to be like writing this block out to a file and then investigating it in a hex editor, because I think that's going to be a nicer way of looking at it than trying to just discern some information out of this buffer. So let's do that. Let's take block 0, and then I'm pretty sure I brought file system in already. I did not. So let's get star as fs from fs promises, and then we can just await fs write file, and we'll call this one well, let's just call it block 0 for now. Alright, run that again. If all goes well, we should write out to a file, so that should be done now. And then let's give ourselves a bit more space. Clear, bewitched, and block 0.bin. Alright, so we've got some stuff here, and well, I guess we're going to need to figure out if this is what we're looking for, but it looks pretty good right now. And I already know that it is good because I've been through the process a little bit, but I want to show you how I got there. I want to show you the steps that I went through, because before I did this, I hadn't ever like played around with FAT32 file systems or anything, so I didn't really know what I was doing. So let's go back to the web for a minute. And we're not really going to get an answer out of this, because this page isn't really specifically about FAT32. I don't actually know if it mentions anything else. No, this is really about the... Oh, it does mention something about file system. Yeah, but this is not really where I figured it out. So I think at this point I was looking at Paul Stoffregen, I think his name is. I'm probably pronouncing that correctly. And Nigel, yeah, Nigel was already on the kind of the trail that we're going to be going down now, because he's mentioned that the last 2 bytes of the MBR, which is the master boot record, should be 55 AA. And if we look kind of at the bottom here, we'll see those 55 AA bytes. So what this actually is, this block that we've read, is the master boot record. And yeah, so that's actually what this page is going to go into some detail about. This is actually a really nice resource as well. Some really nice diagrams that lay out the data structures. So when we read this first thing, what we're going to get is something called the master boot record, and you can read it with LBA equals 0. So that's what we did. For any new projects, you shouldn't even worry about accessing a drive in CHS mode, and CHS is cylinder head sector, and that is of course to do with like literal like cylindrical media where you have like sectors and you're reading on them like that. Like that's very yeah, luckily we don't have to deal with that, but the remnants of that system and the idea of that kind of media is going to be all over this, which is kind of fun. I think it's one of those like archaeological things that if you go digging down into the computer system, you don't have to go very far to start finding stuff that we use in the modern world, which is actually based on like what most people would think of as kind of, you know, older technology and like stuff that is generally not used now. So we can address in LBA, and well, kind of what we're going to see is something that looks like this. We're going to see 446 bytes of boot code. So supposedly what we're seeing here, or if what I should say, what we're seeing here in the hex stub is some code, some x86 code, presumably in a kind of in the 16-bit version of that. I think I could be wrong about that, but I haven't actually taken the time to to kind of disassemble this, but I guess you could. And eventually, yeah, so we get this 446 bytes of boot code. Then we get a 64-byte partition table. So you can partition an SD card, right? And so this is kind of where this is coming into. Like, you can take some sort of physical media and you can partition it into different kind of logical spaces. And that's what we have here. There's going to be one partition on this SD card. And so you're basically partitioning the SD card. An x86 ASM disassembler in JS Next. Yeah. I think you know, there's a never-ending list of projects, and that does sound like a really fun one. Although I have the idea that disassembling x86 is like nightmare fuel. Like I think there are a lot of gotchas involved in disassembling x86. You know, depending on where you start reading an instruction from, like you end up like just pulling stuff that makes no sense whatsoever. Okay, so the last 64 bytes is the partition table, and so the first 446 bytes is the MBR. That means the first 446 is going to be the first byte of that partition table. So we can actually already go down there. If I switch the view to this, so you can see down here in this corner, you can see the offset, and you can have it in decimal or in hexadecimal. This is Bewitched, by the way. It's a hex editor that I wrote on this channel. So, what was it? 446. So this byte here, this is the beginning of the partition table, and that kind of makes some sense because you can actually see that we see data after all these zeros. So, in order for us to figure out what this data means and where we have to go with it and what we're going to do with it, we need to go look at some other resources. So let's kind of follow the rabbit hole down. So there is actually a reference here for a 16-byte partition entry, and it kind of gives you some information here, but I found a slightly better breakdown of this information is if we go onto the Wikipedia page for the master boot record. Let's get that loading in. If we take a look here, then we can actually get a very detailed description of the structure of a modern standard MBR. Hopefully you can see this. Yeah, so we're going to have, if we go down here to these offsets, and the first one, this partition entry, we can kind of take a look here at what this is going to be made of. And so that brings us down to another reference point. Yeah, I know my image is over here, and I'm probably going to be, I'm going to try to keep the my thing out of the table, but this is going to tell us the layout of this partition, and kind of tell us how we're going to figure out where to go from here. So the layout of one 16-bit partition entry, all multi-byte fields are little endian, so that's good to know. Everything we did in the first part of the SD card driver was in big endian, so we have to send commands in big endian, but we're going to be talking to the file system in little endian. So yeah, that's always fun. Mix the endians around. Yeah, so the first byte is the status or physical drive. Bit 7 is set for active or bootable. Old MBRs only accept hex 80 or 0, which means inactive, and 1 or 7F stands for invalid. So if we actually look here at this byte, what we have, I need to move some stuff out of the way, what we have is 0. So yeah, we don't have a bootable drive. And that makes sense, right? We're not booting from this SD card. It hasn't been set up in that way to be a bootable piece of media. The next 3 bytes are the CHS address, which is the cylinder head sector address. And as we know, we can just completely ignore that. We don't need to worry about CHS because we're only going to be dealing with LBA. So we'll skip over that. It is worth, by the way, if you want to get into this and you want to kind of recreate this, I do recommend going down the rabbit holes of these Wikipedia articles and maybe like, looking into it a bit. But in this case, it's not gonna help us. So then we've got our partition type, and there are various partition types. We can see them here. So where is that at? Which byte is that? That is going to be at offset 4 from the beginning. So if we go back to the data and move that, so this is offset 0, 1, 1, 2, 3, 4. We can see that this is the value here we have is B. And if we go back to the page here, B is, it says that we have a FAT32 with CHS addressing, which is kind of funny because that's not what we have, but but I guess that happens. But if you kind of if you follow the line back, what you'll see is there's this column that says CHS LBA. And if you scroll up, you'll see that what this basically is supporting in some way is both CHS and LBA. That's a different one, but yeah, this one also somehow supporting those. So I have to admit, I was kind of confused the first time I saw that, but it kind of, I guess it cleared up in the end. The next is the CHS address of the absolute last sector. And then finally, well, not finally, but penultimately, we have offset 8, which is a 4-byte LBA of the absolute first sector in the partition. And then C tells us the number of sectors in the partition. So what we can do is we can read these 2 values out, and they're going to be kind of the important ones for us. So let's take a look at those. If we read at offset 8, and this partition table starts at, where did it start? Scroll back. It starts at this address. Let's put some of these constants down in the code and start to zoom in on it a bit. So I'm just going to drag that down, and I'm going to, I guess at this point it might be worth starting a class. So let's make like a FAT32 class, and we'll do a similar kind of situation to before, which is we'll take in, like as a dependency, we'll take in some SD card. Instead of taking in the SPI, we'll take the SD card this time. Is this video archived? Do you mean that will this video be available after the stream? If that's what you mean, then yes, the video will be available after the stream. So we're going to have an SD property, which is an SD card, and we're going to take that in the constructor, assign it to this. We will have our own init method. So this is kind of the pattern that I'm building up. Everything has its own async init method, and that way we can actually await the SD cards in it. So we set the SD card up correctly, and then we can start doing the FAT32 specific stuff. But first, we're going to make these constants. So I want to call this MBR, like master boot record, partition offset, and that's going to be 1BE, and then MBR, we're going to want to get the, what do we call this, the LBA first absolute sector offset. It's like an offset to the offset. So absolute, LBA absolute first sector offset, and that's offset by 8. And then we can read that. And then let's also grab the other one, which is the number of sectors in partition. So that one will be mbr num sectors in partition offset. Names get longer and longer. Alright, so now we got these 3 pieces of data. These are things that we can actually store kind of in the FAT32 system itself. So we can read those out. And let's store these as variables. So we want to get the... I guess we don't need to care about this. We need the partition offset. Partition offset, which will just be a number. And we'll just set it to 0 for now. And we can get that. Partition offset is going to be... oh, one of the things we need to do is to... Yeah, so we're doing the read block stuff. And we need to move that read block up here. So when we read this block, that's going to be the MBR. Hello, Vance Jane. Nice to see you. Dude, I just know what the basics of OOP and functional programming are. This doesn't even look like JS to me. Well, technically it's TypeScript, so that's... like, you don't have to feel too bad about that. I don't get this. Is this TypeScript code transpiled to native code? Somewhere down the chain it is, eventually, with a JIT, but that what's happening now just runs in Node. This is just running in regular old Node, nothing special. If none of this is making sense, it's probably worth also at some moment going back and watching some of the previous streams where we built up the kind of the path to get to this point. But basically we're just communicating to the hardware directly, and we're building up abstraction on abstraction till we can actually talk meaningfully about a file system. But what we're actually doing is sending very low level commands to the devices in order to do that. So we're going to read the master boot record, which is at block 0 of the SD card. Then in order to get the partition offset, or rather the partition LBA. Yeah, let's rename that. Let's call that partition... Oh my god, I can't type. Partition LBA. That is going to be in the MBR, and then what we can do is we can read a uint32, and we know that we have to read little endian. What we receive back from this is a node buffer, so we can use node buffer methods in order to read out values in little endian or big endian and different sizes and everything. And the offset here, well, that's going to be the MBR, the partition offset, plus the MBR LBA absolute first sector offset. Yes, that's going to be that. And then also after that we get the number of sectors in partition. So let's call it num sectors in partition. We don't need these other things because we can just assign number in the beginning. And in that case we're doing that. So, you know, this is just a number, this is just a number. We're adding them together and we're reading a specific byte offset, getting a 32-bit integer out of that, and that's going to be our kind of data there. So if we actually just try and work out what this is going to be, let's open up this data again, and this is the 0 point, so 1, 2, 3, 4, 5, 6, 7, 8, and then we're going to read a 32-bit little endian number here, so it's going to be these 4 bytes. And the smallest byte comes first. So this is the smallest byte. And then it's this one. sorry, we actually think of it reading it from the other way around if you're thinking from like the biggest part of the number to the smallest part. So it's 00008000. So that's the number which we should read from this partition LBA. And then immediately following that is going to be another number, which is this one, which is 00EB7000. Which is a bigger number considerably, but yeah, we will actually just have to take a little look there. And let's just log those values out for now. This.partition LBA, make it a hexadecimal number. What are good resources for understanding async await? Have a playlist on this channel. So if you go to the playlist tab, I have 2 videos where I make promises from scratch. So I build a promise implementation out of nothing, and then one which then builds an async await implementation for using coroutines. Sorry, generator functions. So yeah, if you want to find out how they really work on the deep, like inside part, like I would recommend going and checking that out. Okay, so we know that we can read that stuff. We're gonna log these things out. Let's try to run this now. What we should say is C, and let's get rid of this, and let's get rid of the init, because we're gonna do that in the FAT32, so we need to make a new instance of FAT32. We need to pass in the SD card. We need to await FAT32.init, and then that's going to actually trigger off the actions of like doing these reads, getting the master boot record and everything. All right, so let's try this. I'm going to run the driver. I'm not resetting the device because I'm. Alright, yeah, so actually, as you can see, we got the right numbers out, right? We got 800, so that's what we were expecting for the partition offset. So that means we're going to be reading the LBA, so we're going to do a read block, which we've done here, but we're going to be reading hex 800 to get that off, to get the first block. And this is the number of sectors that we have in that partition. And the number of sectors, so a sector is 512 bytes in this case. So if we have this, in decimal, that's that. That's the number of sectors we have. And if we multiply that by 512, that's going to give us the number of bytes that we have in this partition. So that is this number of bytes. If we take that and we then divide that by 1024, that's going to give us the number of kilobytes. And if we divide it again, we're going to get megabytes. And if we divide it again, we're going to get gigabytes. And what you see here is that it's 7.35 gigabytes. Now, this card is actually 8 gigabytes, so there's something wrong there. Like, what's the thing that's wrong? And the thing that's wrong is that like any company that wants to sell you storage space, they will tell you that something is 8 gigabytes. But what they're doing sneakily behind the scenes there is they're not using the gigabyte term that we all know and love, where we're talking about powers of 2 and we're talking about dividing by 1024. No, they use a kind of like they decide that it's going to be a kind of metric thing. And I say that as a lover of metric. But it doesn't make sense in computers, right? Metric is not the right metric for computers. We use powers of 2 here. But yeah, they're saying that actually you should divide by 1,000 instead. So if we divide this by 1,000 each time instead, what we see is that we get 7.89 gigabytes. And that's closer to their advertised space. So yeah, that's kind of kind of one thing to look out for, kind of an annoyance from SD card stuff, but that looks sane. That actually looks like we got a good value for the number of partitions. And obviously you have to remember that there's some wasted space on the card due to the way it gets partitioned, so you don't have every single byte available. Yeah, so that's what we've got. That is looking pretty good. So I think at this point, let's actually go and read the block that's at 800 and see what we get. So we can do that as part of our kind of boot up code. Just pouring some water here. Greg has a question. Do SD cards develop bad sectors like old spinning disks? Yes. Yes, they do. The flash memory is like really, really unreliable. It's like horrifically unreliable. And there is, and I recommended this in the last stream, and I'm going to heartily recommend it again. There is a talk by Bunny Huang and Sean Cross, who I forgot to mention in the previous one. So that's Bunny and Zobs. And they talked about SD cards and kind of going into the gritty detail about like the counterfeit SD card industry in China. And they talked about the fact that inside SD cards there's this tiny little microcontroller, like a tiny little chip, and it's its job to regulate the blocks and to kind of you do something called wear leveling, which is where you avoid writing to the same place again and again and again, because that every time you read and write from the place on the SD card, it becomes less reliable. And so internally, that microcontroller is remapping the different parts of the flash all over the place. It's insane. It's super cool. Definitely check that out. Yes. All right. So at this point, we can just read that block. I'm confident to do it. So let's get the partition block, which is going to be await this.sd.sd read block, and we're going to be reading this partition LBA. And what I will do is something similar to before. Let's just do fs write file, and that's going to be partition.bin, and we will write our partition block. And I think this is just a nice way of doing it, like kind of exploratory style. All right, running again. All right. So yeah, I've still got all the logs, so you can actually see that we've got stuff back already, and that is looking pretty good. We got a different CRC, so we're definitely reading different data. This looks like valid data. This doesn't look like complete nonsense. It looks sort of like normally if you read the wrong place in the SD card, you're just going to get all zeros or all ones or something. It's just going to be like nonsense data. So let's clear and run bewitched on the partition.bin. And that is a really good result already, because this, well, we can see the word FAT32 in ASCII in there. We can see it's got this no name, which is actually the name of this SD card. It's got the magic number that you expect to see in on a FAT32 system, so that's kind of, it begins with this. And maybe this is a good moment to zip back over to Paul Stoffrigen's site again and kind of take a look at what we're dealing with now. So we end up doing all of this kind of stuff, and in the end now we are reading the first sector, and this is supposedly called the volume ID. So this is the volume ID block, so maybe I should actually change the name, and I will do that in a moment. And from this sector, you will extract information that tells you everything you need to know about the physical layout of the FAT32 file system. Just checking in with the chat to see if I've missed anything crucial. Yeah, I see there's some conversation going on about different language choices for low-level stuff. So yeah, well, as you can see, TypeScript is a completely valid choice. It's not like my anyway, I'm not going to go into that. Yes, Nate, Bunny Huang, the Hacking the Xbox author. Yeah, it's a great book. All of his books are great, actually. His the Hardware Hacker book, also heartily recommend it. I may have recommended that to you before, actually. But in any case, to everyone, go and buy and read Bunny Huang's The Hardware Hacker book. Super good. It's like all sorts of, like hard-won tales of manufacturing in Shenzhen and like buying components and hacking things and like reverse engineering. It's like such a good story. Like, just couldn't put it down. All right, so yeah, this is actually going to get some. We're going to get some really useful information here. So basically, Paul gives us a table of useful pieces of information within this, and also mentions to us. Wonder if there is like a breakdown that kind of shows how this looks. Well, this is the entire system, the whole FAT32 file system. So you can see up here we've got the volume ID. Then there is some like reserved sectors. And in those reserved sectors, you can imagine them just not having any data. They just don't hold anything. But in fact, what I think FAT32 does is like copy some information there a couple of times just for redundancy. It's not really useful for us, so we're just going to kind of ignore it now. One thing I should have mentioned, like early on, is that FAT stands for File Allocation Table. So it's like its whole idea is about just having some like table that is going to describe like kind of how the files are structured. The actual structure of the FAT itself is, as Nate alluded to earlier, it's a kind of a linked list structure. So things are pointing to things which are pointing to things. Today we're probably not going to get too deep into that because there's just one file on this SD card. And that's like, in the best case, all I want to do is just read that one file. But yeah, and then eventually you get this file allocation table. There's a second file allocation table. And then there is this clusters, which is the files and the directories. So that's kind of what we're looking at getting at. And apparently there's just a small little unused space on the end as well. And not, that's just a nice detail. There's just a small unused space. So this table, in order to kind of go through this a bit quicker and try to end somewhere on time, I'm just gonna have you take it on faith that we're going to borrow some of these values and we're going to read them out. And so we could just take a quick look, like quick reflection on the data that we see. So there is this Wikipedia article called The Design of the FAT32 File System, which is a really nice in-depth one. And it also gives us this nice overview, and it says that the first region is the boot sector. So if we look at that, this is going to tell us that we would expect a jump instruction. The boot sector has a valid signature residing in the last 2 bytes of the boot sector, blah, 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 then the prior bootloader. So I think if we looked at this, and I think this is true, that we would also see that same 55AA signature at the bottom here, because this is also technically like a place where we could boot from. And this EB5890, I believe that's going to be our jump instruction. Yeah, and then at that point, that's when we start seeing this FSFAT stuff, I think. So EB something 90, yeah, so that's our jump instruction. And then we have the OEM name padded with spaces. So there's a whole bunch of stuff here. I think, what do we see there? We just see MKFS, so that's probably the Linux tool which is used for it's the Linux tool which I use to format this card. So that's looking pretty good, I guess. And then we have the BIOS parameter block, and let's just take a really brief look here. I'm just going to go to Paul's like kind of condensed table in a minute and take some of these, but if you're interested, go and take a look at some of these articles, because they go and explain what all of the different bytes mean. And the first time around that I did this, what I actually did was I just sat with this table open and the binary, and I went through and I checked each byte and I made sure that it made some sense. But yeah, there is the BIOS parameter block stuff. It actually ends up like there are multiple versions of it, and if you scroll through, you kind of need to keep stacking these on top of each other as you go through. But yeah, so what we would see here at offset B, so if we zoom to B, it's going to be the bytes per logical sector, and it's going to be two byte word. So that is going to be at B. So here, the bytes per logical sector, this is little endian. So this is the little n, this is the big N. So it's 0200 hex, that's 512. So what this is telling us is that the number of bytes that we have per sector is 512. And I'm pretty sure that's just common to SD cards. Like it also mentions here, the most common value is 512. Yeah, so that's that. That's looking great. In the interest of time, I will go back to the table at this point. Legacy support is brutal. Hats off for tackling something like this. Yeah, it's I like to see it as interesting rather than brutal. It's definitely, I think, if you grind up against it long enough, it starts to feel really, yeah, probably painful. And I think Nate also has quite a lot of experience with this, doing some homebrew OS stuff, because yeah, I think if you work with a lot of the legacy stuff there that doesn't necessarily make any sense, then that's probably really annoying. So bytes per sector, let's just grab these things out. Like, I'm not going to take this one because as it says, it's always 512. Sectors per cluster, we're going to need that, so let's grab that. That is an 8-bit value located at this offset. So let's put some of these things into constants. We're actually in the FAT32 now, so we can make our constants prefixed with that. So FAT32, this is going to be sectors per cluster offset. I think that was what it was called, right? Sectors per cluster. And then we're going to have the number of reserved clusters. That's going to be at 0e. So num-reserved clusters 0e. Then we get number of FATs. Always 2, so we'll just hard code that. Sectors per FAT, that's going to depend on the disk size, so that's a 32-bit integer at offset 24. Sectors per FAT, so sectors per FAT 24. And then we get root directory first cluster. That's at 2C. Root directory first cluster. Sorry, I realized this is just a lot of like copying and pasting offsets, but it's important when you're doing this stuff. This is some of the annoying part. You know, you're just, a lot of your time is spent just like copying numbers and checking you know, the number of bytes things take up. And then we get a signature, and this is always A5. Yeah, so we don't need to care about that. What Paul mentions is that when you get these fields and you kind of get them down, you can boil them down to a couple of variables. And what makes this useful is once you have these variables, you can do everything in terms of LBA, and you can just like if we want to like read specifically from somewhere on like in the FAT file system, we can just use these 4 variables. So what I'll do is I'll copy these and we'll just kind of plonk them into our code. So we don't need to write that anymore. And these are like C variables at this point, but they're just additions and stuff, so it's nothing for us to worry about. So I'll make these as constants first, and then we'll just transfer them afterwards. So the FAT begin LBA, that's going to be the partition LBA begin. Well, we know where that is. That's the partition LBA plus the number of reserved sectors. The number of reserved sectors, that is something that we need to read from the MBR. Are those offsets relative or absolute? In this case, these FAT32 offsets are absolute, and the MBR offsets that I made are a mix of absolute and relative, which is just absolutely devilish, and I apologize for that. But that's something to fix at some moment. So yes, we need to read this number of reserved sectors. So that is in the MBR, and I thought that is the number of sectors. So let's go back. Let's figure out what that is. If we go back to the master boot record, it's going to be here somewhere. So partition type, number of sectors in partition. Oh no, this is part of FAT32. So the number of reserved sectors. Let's see. Reserved. Oh, it's just one of these. Oh, unbelievable. I thought it was somewhere else, but okay. So that means we need to grab that first. Once num reserved sectors. So in order for us to get that, we need to read from the partition block. So we're going to read, and I think it was a 32-bit value. Number of reserved sectors, 16-bit value at that offset. So read UN 16 little endian FAT32 number of reserved sectors. Cool. And then when we have that, that is where our FAT LBA begins. All right, and then the cluster begin LBA. Cluster begin LBA, and it's nice to have these LBA values. It means that we can just literally just go and grab something from the from an SD block. Super easy. So it's the partition LBA begin plus the number of reserved sectors. Well, that's actually just the FAT begin LBA. And then plus the number of FATs times the sectors per FAT. So in order for us to get the number of FATs, that's going to be, we just read that from here, right? Sectors per cluster, number of reserved sectors, sectors per FAT, number of FATs. Where did we get the number of FATs from? Oh, it's always 2. Yeah, it was always 2. That was the thing. So it's this times sectors per FAT. Yeah, that's something we actually need to get first. So sectors per FAT. Yep, so now we've read that, we can actually FAT begin cluster 2 times the number of sectors per FAT. Alright, so then we've got the cluster begin LBA. and then we get the sectors per cluster, which is just reading those things. Okay, so these following ones, they're not sectors per cluster. That's going to be just reading. Oh, I should check. I'm probably reading the wrong size thing. So the number of FATs, the sectors per FAT is a 32-bit integer, so that would have given some trouble. Sectors per FAT, uint32. Sectors per cluster. Sectors per cluster is an 8-bit value, so that's good to know as well. So that's going to be partition block.read uint8. There's no endianness involved when you read 1 byte. FAT32. Sectors per cluster offset. Okay. And then just the last one, which is the root directory first cluster. Root the first cluster. Partition block dot read, and I think this one was a uint32. Sorry, I keep switching to that unoccupied thing. Yeah, that's a uint32. Read uint32, little endian, FAT32. Alright, so now we got a bunch of useful values. Let's see, do we have a diagram here? Because once we have this, we've got these numbers, and Paul has this nice a nice formula for calculating an LBA address. So an LBA address of something in the something that's happening is going to be the cluster begin LBA, which is the value that we just calculated, plus the cluster number -2 times sectors per cluster. So this is going to be how we figure out which LBA we're going to talk to. Yeah, but that's something for in a bit, because we first need to like take a look in the root directory. I think that's going to be our next logical step. So let's actually turn all of these into variables up here. And then we need to do that and that and that. Okay, but now we have all these numbers, and the next thing is going to be to read the root directory. So let's do that. The root directory. And I'm racing through this a bit, I know, but the root directory is like we get the file allocation tables up first, and then the root directory comes after that. And the root directory is actually the thing that tells you kind of what files are available. The FAT is a data structure that is kind of telling us how, when you go from one file that is a directory, like how you're going to go into another directory or something like that, or how when you have the first piece of the file, you're going to get to the next piece of the file. But right now, we're just going to take a look at the files that we have, because we're not going to have to do any of that for this one file, the test file. So let's await this.sd card sd read block, and the block we're going to read is this root directory first cluster. But now we need to use this formula that Paul mentions, which is to get the LBA, we need to do this. So it might be worth making a function for this, because we're probably going to need to do it in a couple of places, but for now I'll just do it here. So that's going to be the this.cluster begin LBA plus this.root directory first cluster -2, because we need to do -2, and then we're going to multiply by this sectors per cluster. that should give us our root directory block. And then what we can do is, well, let's just do the same thing. Let's just fs.writefile root directory.bin and root directory block. Okay, let's run this. Watching the device blink all of its lights, and that's looking good. We got some valid looking stuff here. Let's make sure it's really valid by opening it up in Bewitched. So that's going to be the root directory bin. And well, of course, you all don't know what is on this SD card, but I know that there is one file on this SD card, and it is named bootrom. And so that is the file on this disk. This was a really big moment for me when I kind of like finally got to this point. I was like, oh, this is really real now. I'm reading the name of a file on this SD card by, you know, sending all of this information to it. So this is the file we're going to try and get. But you'll see that we've got a whole bunch of data here, and it's kind of not really clear what the data means. And eventually it's all zeros, but there is some stuff in here. So what does this mean? Of course, we'll go back to this useful resource of today. And yeah, this is a very nicely written article, so it's worth going into. So in short, what we have is a series of data structures, all of which are 32 bytes long. They start with a short file name, which is 11 bytes long. Then they have an attribute byte. Then they have some stuff here that's meaningless, apparently. They have a cluster high. So the cluster, remember we use the clusters. We can turn those into LBAs, which we can ask for blocks from the SD card using an LBA. So this is the first cluster high and the first cluster low. So we kind of need to put those two things back together. And then we get the file size, which is a 32-bit integer. So obviously at this point, we're not building all the real APIs, but what I actually want to do is get to the point where we can see the information about this, this file in particular. So let's actually just get this stuff out and see if we can get the information, and finally see if we can read the stuff out of it. So yeah, first of let me see what happens if I copy this into the code. Is it gonna explode everywhere? Because that would be less than useful. That's not bad. That could be worse. Alright, so let's just do it like that. And I guess we could try and correlate this a little bit now while we have it open. So so we get 11 bytes, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the first 11 bytes, you can see that it kind of gets padded with spaces at the end. Need to bump this up just a bit more, and then we can roll that up. So when we get to byte 11, that's the last, this is the first one. So after that, of course we can just read this table. So we get the short file name, which is 11 bytes, then we have an attribute byte, which is 8 bits. So this 20 is revealing some attributes. Maybe we can actually take a quick look here, because there is an attribute table below. And hex 20 means that the only bit which is active is bit 5. That means this thing is an archive, which translates to has been changed since last backup. So in this case, this this has been changed since last backup. You know, but I guess there's some meaning in that in terms of the file system or something, but it doesn't really have any meaning for us. But there are some useful things in here. For instance, you know, read only. So the file system should try and prevent like should actively prevent you from writing to this. Should not show as a directory listing, so it's hidden. File is operating system. I guess that could indicate that this file is like some compressed operating system or something. It gets its own bit, so it's probably important. File is a volume ID. It is a subdirectory, in which case we're going to have to do something specific with it, and then this archive, and then the last two don't get used. So that's kind of the attribute byte that we see there. Then we get the first cluster, which is a 16-bit value starting at this address. We get the cluster low, that's a 16-bit value starting at that address. And finally we get the file size. So let's actually, first of all, let's put these as constants, because that is nice to do. Let's just cut all of that, and we'll bring it up to the constant area. And the first will be FAT32. This is going to be what do we call this? Root file name. And these are going to be relative offsets, because we're going to always be talking about like which. Actually, does Paul give us a name for these things? Which would be a better choice? Directory data. Maybe we could call this a directory entry. Maybe that's kind of a bit clearer. So we're going to have the short name offset. Well, that's just 0. Then we're going to have the... Yeah, we should put the offset for these as well. Then we are going to have the attribute. And the attribute is at B. And then we're going to have the first cluster high, then the first cluster low, and we need to write the right offsets here. So that one is going to be 14. That one is going to be 1A. And finally the file size. Yeah, I've made a mistake here. So these should have that. Directory actually should have entry as well. Right, and the size is at C. And yep, okay, so those are our constants, and yes, so let's go back. I'm going to copy that block again because I got rid of it. I realized that I'm not checking the chat very much, so maybe I should quickly check in. What's happening? Thanks, Greg, also for being on top of it. Yeah, there's a discussion going on about engagement and the best places to stream and stuff. And for me at the moment, I'm just doing this for fun, and because this is an easy format for me to now make these kind of videos, and especially working with the Bus Pirate. So at some point in the future, maybe I'll look deeper into other options, but for now, this works pretty well. And in the end, kind of the video that comes out at the end of it, you know, that people can watch online, that's more the that's what's there forever. So that's kind of it's nice to have people here in the same time and to be able to chat. Actually, it's really nice to be able to have people who are kind of over the shoulder and giving debugging advice. But yeah, so it's more like, you know, this will end up becoming a video, which, even though it's very long, will be watchable on the channel, if people want to do that. All right, let's actually get this information out. So we want the file name, and well, we're just going to get the first one, right? So we can do this with toString. This is something you can do with buffers. So what we will actually say is that the encoding is going to be ASCII. I'm pretty sure it's going to be ASCII in this case. And the start is going to be 0, and the end, well, it's going to be 11. We know that file names are 11. So this is kind of, we're not really using the offsets here, but it's okay for now. Then we are going to get the attribute, which we've already seen is 20. So we can get this with read uint8. The offset for that is going to be FAT32 directory entry attribute offset. And then we're going to get the cluster, let's call this file cluster high. And that's going to be a uint16, I believe. A 16-bit integer, yeah. So I don't know why that isn't together as a as just like one 32-bit field, but for some reason it's kind of it's split into these two things that we're going to need to reassemble. So FAT32 first cluster high offset. Then we can get the corresponding low offset. Yeah. And then we can just get the file cluster itself, which will be the file cluster low ORed with the file cluster high shifted up by 16 bits, right? Because they're both 16-bit values, we push the high part up top. That should make sense. And then we can get the file size. And that is going to be a 32-bit integer, I believe. 32 bits, yes. File size, read uint32, FAT32, directory entry, file size offset. Yeah, cool. Let's log a bunch of this information. In fact, let's just do it like do it like this for now. Just to see what comes out of there. So let's run the driver. I'm really impressed with the fact that this is working with the software reset this time. Okay, look at that. File name boot ROM, attribute 32. File cluster high was 0, file cluster low was 3. The file cluster turns out to be 3, right? Because there's no upper part. And the file size is 13 bytes. That sounds about right, because I know what I put in that file. Alright, so the kind of real moment of truth then is going to be reading the block that represents this file. So the file block is going to be await this.sd.sd read block. And when we read this block, we're going to kind of need to go through this formula again. So we definitely should make something for this. But this time we're going to use the file cluster instead of the root directory cluster. So that's going to give us the block. And well, if we take a look at Paul first, directory entry, I don't know if he mentions a file in general. Well, I'm going to what I'm going to do is I'm not even going to write it out to the file system. What I'm going to do is I'm going to get the file contents, and we're just going to say that that is going to be the file block toString, it's a text file that I put on this thing. So file to string, and we're going to say that it's ASCII encoding. It's UTF-8, but it doesn't actually matter because it's ASCII just in text form. We're going to start from 0, and we're going to go up to file size because that's what it is. And so that file should fit in this first cluster. So let's actually just console log the file contents, and I'll be so happy if this works. All right, so what do you know? We've got the file out. So there it is. That is the contents of that boot ROM file for now. It will at some point be a boot ROM for the Game Boy, but right now it's just the text "Hello World." So if we go back to the goals of this episode, the goal was to read the contents of a file located on an SD card, and we have achieved that. There's cleanup that needs to be done in the driver. We need to like clean up stuff in the SD card driver, but also in the file system layer. But I think this is a really good start. So yeah, I'm personally really pleased with this. It's coming along. Thanks for joining me. Joining me with you guys, checking along, and yeah, I hope you have a wonderful weekend, everyone. And yeah, I'll hopefully see you next week when we will be continuing with file system shenanigans. Yeah, so that's about all for now, and I'll see you next time.